Computers are everywhere these days, aren't they? I mean, they're in desktops, laptops, consoles, speakers, watches, washing machines, door locks. The list goes on. Your smartphone even has three of them. They let us do some awesome stuff like landing rockets, getting a robot dog to piss on its creators, or spending way too much time playing video games. I wanted a nice, straightforward project to make up for, well, to be productive. So I decided to take a few days and design my own computer processor. I've described a computer as a device that operates on memory. So let's start there. This is a 64-bit wide by 1024 row memory that I created. It's honestly a little bit overkill, but I like having the space for future development. I originally wanted to make this intrinsically multi-port memory, but Vivado kept complaining that it wouldn't fit in block RAM, even when I explicitly told it not to infer the module as block... Okay. I promised myself no ranting about Xilinx. This memory has one interface. Moving on. Wrapped around this module is a memory controller block. This piece of logic interacts with all the other blocks, orchestrating their memory access in a round-robin fashion. Technically, there is a request grant access interface, but I kept things simple for now. The peripheral control block loops through all the system inputs and outputs, in this case 4 switches and 4 RGB LEDs, and writes input values to a dedicated memory address and reads output values from a different memory address to drive the LEDs. I'm using 512 for the LEDs and 513 for the switch states. For me, this is a standalone block that talks directly to the explicitly defined memory locations, which you or may not see elsewhere in different architectures. And finally, the pièce de résistance, the CPU. I sometimes refer to this as the ALU, the arithmetic logic unit, but that's technically incorrect. It's one part of what makes this thing tick. The processor is the module responsible for actually manipulating the memory. This means it has to, 1, pull data from said memory into its internal registers, 2, manipulate that data in some predefined way, and 3, push this newly computed data from its internal registers back out to the memory. We specify what data the processor needs to pull and how to manipulate it by writing a list of instructions that constitute a program. These instructions are stored in the memory. Now, you may wonder, how does the processor know what to do to the memory if the instructions are also in that memory? Well, the CPU has an internal register that always holds the location, the memory address, of the next instruction. This is the program counter. It's reset to 0, assumed to be the start of the program, and usually just increments to the next value, but more on that in a second. This counter value is all the CPU needs. It feeds directly into a loop that is always running. Fetch, decode, execute. In the fetch state, the CPU takes the PC value and drives it onto the memory interface as a read request. The data at that memory location is the next instruction, which the CPU takes and stores in the instruction register. But this is just a big binary jumble. We need to decode it. This binary string is machine code. Machine code is essentially the same as assembly, just translated from human readable format to a computer readable one. Computer readable means the instruction can be split apart and piped into the combinational decoder circuit, which will tell the CPU logic to execute your desired task. This can be pretty complicated in modern machines. I kept mine pretty simple. The first bit is the register select, which indicates which of the two caches to use. The payload is an input value for the task at hand, and the opcode specifies the actual task to perform. Each opcode corresponds to a dedicated logical circuit, and it is used to select which logic path to execute. The instruction set is the list of all operations physically implemented on the chip. I thought about implementing the OG x86 set, or maybe even the RISC-V set. I got halfway through reading the documentation before getting bored and deciding to just make my own. Fox 2022, keeping things simple. As part of the execute stage, the PC may point to a specific address, meaning a specific instruction, using a conditional or unconditional jump command. These allow for conditional branching and code reuse through subroutines. Otherwise, it just increments to point to the next location in memory, executing the code sequentially. And then we restart with fetch. So, write it all up in HDL of your choice. I used Verilog. Using your toolchain of choice, I have to use Vivado. And then you can look at this confusing barrage of waveforms in simulation to see that it works. But it is way more fun to actually deploy it into actual hardware.
Yes! It works! Yes!
Here you can see it running a 2-instruction program that turns on the LEDs. If you don't know, you're asking, what is this thing and how did you deploy your design so quickly? This awesome little device is a field programmable gate array, or FPGA. There's a good chance you've heard of those, even if only as a tech buzzword. So what in the blazes is it? These are reconfigurable digital devices created in the 80s by the co-founders of Xilinx. Digital loosely means operating with binary values represented as electrical signals. A digital circuit takes a bunch of these signals as inputs and generates a bunch more as outputs. These circuits are traditionally single purpose and printed directly into silicon. So let's start by taking a closer look at a very basic digital circuit like this one. It's got 2 inputs and 1 output. Since they're all binary, each input can be one of only 2 values, 0 or 1. Consequently, there are 4 possible combinations of inputs. A digital design engineer has to determine what the output value should be for each combination, then fill the box with the necessary hardware to make that happen. One way to do this is to have 4 programmable memory elements in this box, each one corresponding to one of the input combinations, which can be filled with the desired output value for that combination. These can then be passed through a selector switch logic that chooses which memory will drive the output value based on the input values. This may not be the most efficient solution, but it has the benefit of being reconfigurable. The memory values can be updated whenever the designer wants to implement a different logical function. Any logical function that fits the number of inputs and outputs in this block. While you can expand these lookup tables, or LUTs, in size, increasing the number of inputs or adding parallel outputs, on their own they're only half of the equation. Our modern problems require modern solutions. The logic we need to build are far too big and far too complex to fit in just one of these blocks. Now, the beauty of digital logic, and more broadly in engineering, is that these problems can be compartmentalized. They can be broken down into smaller, well-defined chunks that can be developed separately and then recombined at the end. You can repeat this process until you get chunks that do fit in a LUT. Then all you have to do is combine all these LUTs together into a network that satisfies your original design requirements. That's the second half of the FPGA equation. The creators placed a bunch of these configurable blocks on a grid of interconnects and then made the connections themselves configurable. Each intersection could be connected or disconnected to route the output signal from one block to the input signal of any other block. So, as long as the digital logic you're trying to implement isn't too large, anything can be algorithmically converted into a combination of LUTs and interconnect configuration data, which is then encoded into a bitstream file that is used to program the physical device. While there are speed and efficiency trade-offs, the underlying technologies have gotten so good that they're rarely a concern. Over the decades, these chips have gotten larger and increasingly complicated, adding dedicated transceivers, making the LUTs more complicated, adding dedicated circuits for common functions like multiplication. even processors or AI engines. Modern chips have a ton of fancy features, like the Versals, which I'm personally not a big fan of working with, but I said no Xilinx rants. Okay, where was I? I designed a computer, had Vivado run the synthesis, implementation, and routing, then deployed the design to my Artix A7 development board. Now I just need a program to actually run on it. A good example, I thought, would be a script that rotates through each LED, turning the RGB channels on or off for that LED based on the switch values. From a high-level perspective, this sounds pretty easy. But remember, I'm working with only these instructions and need to directly control each memory address I want to use. Coding at this level is a little different than with a high-level language. For example, in a high-level language, you should never use goto statements, but here you have to. Jump statements are the only method of control flow due to the nature of the processor logic. So my program. First, I need to initialize the memory locations I want to use as variables. I have two variables and then a third constant. The variables are a timing counter, so I know when to move to the next LED, and then a selected LED tracking variable. Next, I need to begin my main loop by loading the counter value, incrementing it, and then either jumping to a counter reset subroutine if the counter has hit the max value constant, which also increments the LED select value, or I have to store the new counter value, and then we can move on to managing the LEDs. Here I need to, 1, load the software peripheral register into the cache, mask out the switch 3 button's value, then load the LED select value to branch the execution path depending on which LED is being set. Now the LEDs are controlled by the 12 least significant bits of the LED peripheral memory address value. I need to take the 3 switch bits that are in the cache and then write them to the correct spots in the LED bit stream, which was a little tricky. I accomplished this by using an LED specific AND mask to clear out the correct 3 bits. Then I would shift the switch values so that they lined up with that gap. And finally, I can just add the two values together. Since I know that the LED bits are 0, 0, 0, adding will only overwrite these 3 bits with the switch values, leaving all the others alone. Then I can manually store the new LED values and jump back to the beginning of the loop. I wrote the code for this out in assembly shorthand, which meant I needed to convert each instruction to its binary representation. This required writing out each bit field's value as machine code to be typed up and loaded into memory. Generally, you would write a piece of code called an assembler to do this translation for you, but as is tradition, I did this all by hand. And, as always, there were a bunch of dumb mistakes that took plenty of time to debug. For example, at one point the LEDs all updated simultaneously, which was confusing because the simulation all looked right. This is actually because I was incrementing the LED selector value every cycle instead of waiting for the counter to max out roughly every second. So it was rotating through the LEDs just so fast that I couldn't tell. You'll also notice that the red LED isn't working. And this is a good chance to show you my debug process. So first, I run the simulation and try to recreate the problem. Since this is a functionality error, I can get away with using the behavioral simulation. You can force signal values to recreate the issue. Here, even though the red switch is high, the output LED value is staying low. So we go and we start tracking the signal through the system. The peripheral memory address matches the LED output, so I go and I look at the ALU next, and this output value also matches. So then I have to go through the fetch, decode, execute cycle for each instruction in this part of the program that calculates this value. And here, the switch values are read improperly, but the third switch value is being masked out. And you can see that the payload, which contains the bit mask, was set to 3, which is binary 0, 1, 1, and it's supposed to be set to 7, 1, 1, 1. Fixing that in the code fixed the red LED issue. I was lucky here in that it was just a programming issue. But you can also run into hardware design problems, and these require changes to your actual HDL. We minimize these by writing test benches for each module. For every block that I discussed in the beginning, I wrote a custom test bench file and tested that block on its own. Writing a good one is a real art, and the more well-defined the function is and the more rigorous the testing, the fewer problems you'll run into at the end of the project when you're integrating and trying to run the whole system. I was pretty lax about it here, and I rushed to deploy, so I had to spend a decent bit of time just debugging the system. But I got it working. My very own CPU. I've got a lot of plans for you, little guy. This is the start of something big. I can feel it.